Assalamualaikum warahmatullahi wabarakatuh. So this is my group 1 for assignment control principle. Okay, so we move to next part. So this is our group member. I punya member group untuk assignment control principle. So the first one Nur Ariana binti Ahmad Azmizi, and the second one Nur Maisarah binti Hazrid Fairuz. Then the third one Haziq Ashraf is me, Muhammad Haziq Ashraf bin Nabi Amin. So yang keempat Vanishwari anak perempuan Kini Raja. Then yang untuk kelima, the last one, Syarini anak perempuan Bagunan. Okay, so we move to next part. Okay, so this is our group punya Gantt chart. As Dr. Ahmad Faiz can see, the yellow one belong to me, I yang buat. Then the green one Maisarah, the blue one Vainis, the red one Shalini, and the blue biru cair adalah Adriana. Okay, so we move to next part. So introduction for assignment control principle ni adalah electric mechanical control system combine electrical and mechanical part to control machine automatically. It use sensor to detect condition, controller to make decision, and the system improve efficient, precision, and the productivity across industry like manufacturing, robotic, aerospace, and automotive. Then lastly, they can operate continuously with a minimal human input and making them key to modern automotive and technology.
Hi guys, I'm Sarah with number card metric of B1223, 102 and 17. So I'm going to continue with my part, which the block diagram of the plan that visually represents the relationships between inputs, outputs, and the control mechanisms, providing a clear overview of the system operations. This section serves a foundation for the subsequent analysis, illustrating how the system is designed to achieve desired performance metrics such as stability and responsiveness. This diagram highlights how the electrical and mechanical parts works together. So, for the time domain analysis part, uh, in the time domain analysis of the plan, the system's performance is evaluated over time. Key parameters include rise time TR of 0.18 seconds, peak time TP of 0.315 seconds, and setting time TS of 8 seconds. The system has an overshoot OS percent of 85.45%, and a steady state error SSE of 0.909. These values show how the plant performs and where improvements are needed.
About stability analysis of the plant. The plant is tan over s square plus s plus 100. S power of 2, we can see that in left half plane 1 1 100 10 and 1 equals to 100, and the right 100 0 1 0 1 0 1 equals to 0. Here the right half plane equals to 0 and the left half plane equals to 2. It means system is stable. General block diagram starts from input, that is desired parameter, and following with error detector, controller, actuator, plant, output, actuator parameter, and sensor. Here, this block diagram demonstrate how a closed loop control system function to ensure that the output aligns with the intended goal. The process begins with the desired value input, which is compared to the actual value feedback by an error detector that calculates the difference known as the error signal. This error is then transmitted to the controller, which determines the necessary adjustments. The actuator applies these corrections to the system being controlled, the plant. Meanwhile, sensors continuously monitor the system's output and relay the actual value back as feedback. Forming a loop, this mechanism enable the system to continually adjust and reduce the error to reach the desired outcome.
name is Shalini Bargunan and my metric number is B122310531. Now I'm going to explain about the electromechanical drawing of the control system. The mathematical modeling represents the study and design of an electromechanical control system. The process begins with the derivation of the electrical and mechanical equations that characterize the system's operation. After that, the system is mathematically fully represented by the integrating the formulas. A systematic method for analyzing signal flow graphs Manson's rule is applied to determine the transfer function of the system. The electrical component that has been chosen consists of an inductor of 2 micro, a capacitor of 2 microfarad, and a resistor of 1 kilo ohm and 5 kilo ohm. In the block diagram, these electrical parts stand in for the controller. The components selected for the mechanical portion are a 0.01 kilogram mass, a damper with damping coefficient of 2 Newton, and a spring that has 1 Newton spring constant. Furthermore, the DC motor has a back EMF constant of 33.3 and the tachometer has a time constant of 0.7 second. The automatic iron, the plant shown in the block diagram, is represented by the mechanical component. Last but not least, the low back EMF motor serves as an actuator and the tachometer as a sensor. Next, this is the hardware costing. The component we used are mass, damper, spring, inductor, resistor, capacitor, low back EMF DC motor, low feedback tachometer. The total hardware cost is Rm 44 ringgit 80 cent.
Assalamualaikum, my name is Nur Adriana binti Ahmad Azmizi and my metric number is B122310265. Okay, so I will explain about my part on mathematical modeling. So the first one is controller. So as you can see, the equation is there, the formula equation is there. So the RF, our RF value is 3000. Is equal to R1, R2 and R3 plus all the third of resistor equal to one resistor is equal to 1 kilo ohm, and we addition all the resistor, so we got the 3000. And then for the inductor value is 1 mH, and for the capacitor value is 1 microF. And then the actuator, we use the low back EMF DC motor. So the value is 7.5, and our plan is 10 over S kuasa 2 plus 2S plus 100. And that's all for our mathematical modeling.
So I'm going to continue with the overall transfer function part. So for the overall transfer function of the electromechanical control system is derived by integrating the electrical and mechanical equations that define the system's operations. This process utilizes Mason's rule to analyze signal flow graph, which helps account for feedback loops and for paths, ultimately establishing the total transfer function. The transfer function is crucial for evaluating system performance metrics such as rise time (TR), peak time (TP), settling time (TS), and percentage overshoot percent (OS). For example, the rise time is calculated using the formula of TR equal to 1.8 over omega n square root 1 minus zeta squared, with omega n equal to 10 and zeta equal to 0.05. So the rise time is approximately 0.18 seconds. So the percentage overshoot can be calculated as we substituting zeta equal to 0.05 yields and overshoot of about 85.45%. This transfer function provides a comprehensive understanding of the system behavior and performance in response to various inputs and disturbances. That's all from me.
Here, now I'm going to explain about the time domain analysis of the control system. After we get the OTF, that 1.428 s over s square plus 1.904 times 10 6 power of 6. Here the omega n equals to 1379.85. Then we know that 3r we get 1.08 second and 3d equals to 0.35. The overall is 1% and the C maximum equals to 1.01, and the TP we get 3.6 second, TS 4.2 second, and lastly SSE we get 0.796.
Now we're going to see about the stability analysis of the control system. The table shows that all the first column values are positive, meaning there are no roots in the right half of the S. Since all roots are in the left half is 2, the system is stable. Stability is confirmed and there are no positive real roots.
To conclude this project, our project successfully showed how to design, build, and analyze a control system for the given plan. By following the project requirements, step by step, we created a system that improved the plan's performance, especially in stability and time domain response. The block diagrams and mathematical modeling help us understand how the system works and make it better. The time domain analysis proved that our control system met the expected goals, such as faster rise time, shorter settling time, and a very small steady state error. And that's all. Thank you.